transition to state Q2. And then similarly as here, make another transition, but this time to R. Ignore the input string, ignore what's on the top of the stack, which is now Y, and push X. Okay, so now on the stack you've got X, Y, Z, with X on top. Okay, so with these intermediate supplementary states, if you like, these together result in you're now the machine, the automaton is now in state R, just as here. On the stack has been pushed X, Y, Z, with X on top, Y, Z going down, right? Which is what this is. Now, you may ask, what's the point of this shorthand? Well, it's very useful because what are we trying to do? We're trying to create an automaton, a PDA, that behaves like a grammar. And what do grammars do? Well, they use substitution rules. They look at a variable and they replace that variable with a string, a string that's on the right-hand side of the substitution rule. And on the left-hand side is the variable that equals the variable on the stack of your PDA. Okay, so it's useful to have this shorthand because you've got a string here, right? And that's what we're doing. We'll be substituting, we'll be throwing out a variable on the stack, and we will replace it with a string on the stack. Okay, so this is useful. That's the motivation. That's why we're doing it, right? So this is just the label of these two diagrams. It's how to. This is shorthand, but how to actually implement it, how to make it, build it. Well, like this, with extra states, and you'll have the number of transitions will be equal to the number of symbols in your string. Okay, so this would be your U here, the string U. Your string now is X, Y, Z. And you're going from state Q to R when you're reading on the input string A, and when S is at the top of your stack. So pop the S, push X, Y, Z, and change your state from Q to R. All right. Okay. So that's with that shorthand. Now we can get onto the formal description of this PDA, this non-deterministic PDA. Now, it's a PDA, it has a stack, and it's typical of well, not typical, it's the nature of a push-down automaton. It has a stack. That's what push-down sort of means. So it'll have a sixth variable in its formal description. Before our finite automata, their formal descriptions were 5 tuples. Well, PDA is a 6th tuple because you have a sixth factor, another factor, and that is typically you'll have an alphabet for the stack. The allowed symbols you can push and pop onto the stack, right? And your transition function delta will change. And they'll have, like, as input, they'll have like 3 parameters, and they'll output 2 parameters. Well, actually, a set of ordered pairs, paired like 2 parameters. Okay, right? So we need now to specify those six things in the 6th tuple for the formal specification, formal definition of the PDA we're trying to create, to construct, to build, that behaves like a grammar. Okay, we're trying to show this this PDA exists, and it this PDA, it will recognize the same strings that the grammar generates. Okay? A grammar generates and an automaton recognizes. Well, an automaton either accepts or rejects a string, right? But a language is just a set of strings. So if a PDA accepts all the strings in the language, then that PDA is said to recognize the language. Whereas a grammar generates, using substitution rules, generates all the strings in that language. Okay? So if the PDA is recognizing the language, in other words, accepting all the strings in that language, then we're talking about the same language. So the grammar and the PDA are equivalent because they're describing, using a generic term, they're describing the same language. Hence, they're equivalent. That's what we're trying to prove. We're trying to construct. We're trying to show. We're trying to prove that you can construct a machine, a PDA, a non-deterministic PDA that can recognize the same set or class of languages as the grammars. Or if you keep it specific, for a particular grammar there will be a particular non-deterministic PDA. The grammar will generate a certain set of strings, language in other words, and the PDA will accept each string in that language. Okay, I hope that's clear. All right. Okay, so let's start with the formal definition of the PDA. It's 6 tuple, in other words. Let's start with a set of states. You have Q start, Q loop. What's this? Well, you probably remember in the proof idea, we had like three main steps. In the second step, it said repeat infinitely. Well, when it's doing that, the PDA will be in the state Q loop. It's looping through this. What's going on when it's looping? Well, you're substituting. You're looking at a. Well, I'm getting a bit ahead of myself. It's here, but you're looking at the top of the stack. You're seeing a variable, and then you go looking in your rule list for a substitution rule, where the left-hand side variable is equal to the variable at the top of your stack. Now there may be several of them, in which case you split. You'll make multiple copies of your PDA, and you'll push onto the stack of each one of those multiple copies the corresponding right-hand side of the substitution rule that you're pushing. Right. Okay. Okay. So Q, the set of states. So Q loop and Q accept unionized with another set E. What's E? Well, it's the set. No, it's going to be a set because union, is applicable to sets. E is the set of states you need. Like they're the intermediate states. They're like these queues. And so you put into set E, you'll put all these queues that you need for doing this kind of thing. So it'll depend on what your grammar is. How many strings will you need to pop? How many symbols in the string, and hence you can calculate how many of these intermediate states you'll need, and whatever it is, you pop them. Sorry, you will. Don't be confused. You will put them into E. I just use pop in ordinary English, but it's confusing because in this context it has a very specific technical meaning. pop. Maybe it's more Australian slang. It just means put into or place, okay, or add, or insert, whatever. Right. Okay, start states Q start. It's pretty obvious. There's only one accept state. It's Q accept. Okay, that's all you need. Now the transition function. That's always the hardest part when you're defining a PDA. It's defined, well, it'll come out of this. Let's see how far do we get. It's about another, well, two half squares. Right. So as we go through this piece by piece, the delta, the transition function will be described. Okay. So. So in a sense, your transition function, that's the set of rules telling you what the next state is and what you push, which strings you push, and you have a set of them for each transition. Okay, so for now in the proof idea we had three main steps. The step one was just initializing the stack. In other words, putting $1 on the stack. Okay. So now writing. You can write the transition function delta with these three parameters equals, and then a wiggly brackets for a set, and then we'll have an ordered pair or more. On the right hand side, it's like here in this form. Okay. Now remember, it's a non-deterministic PDA, so the transition function returns a set of ordered pairs. In this case, there's only one member in the set. Okay. Now can you see what's happening here? We start on the start